Okay, welcome to section 8.7, complex numbers, not to be confused with complex fractions. Complex fractions are very straightforward. They're complex because they're big, they're not very entertaining. Complex numbers, that crap is crazy. That is probably, in my opinion, one of the coolest parts of mathematics. So this is where I'm going to geek out a little bit. I love complex numbers. I love imaginary numbers because they are unlike any other numbers you've ever seen. In fact, you're never going to see them. You may or may not have heard about I before in imaginary numbers, but before we dive in too much, let's take a look at this chart right here. Notice up at the tippy top, they've got the complex numbers. And because complex numbers are both real and imaginary, and we'll dive in again to that in just a sec. But then underneath, you've got two different types of numbers. Real and what we call non-real complex or imaginary. Imaginary numbers. And then after that, everything else, integers, rationals, whole numbers, composite numbers, that all falls under the real realm. Those are all branches of this right-hand side. Nothing is underneath the imaginary numbers, except for one thing. Now that's up for a little bit of a debate whether there's only one imaginary number or multiple imaginary numbers. In my opinion, I say one, because there's only one thing that's purely imaginary. Only one thing that is purely imaginary, and that is the square root of -1. There is no way to write the square root of -1 on a number line. It doesn't exist. It doesn't exist in the real world. There, on our number line, our real number line, you cannot find the square root of -1. It just doesn't make sense, right? How can you square something and have it be a negative number? That doesn't make any sense. Yet at the same time, the square root of -1 has to exist. It has to. If you get up into higher level mathematics, the higher you go, you find that the more you need that thing to be a real thing. You need that thing to exist. So it doesn't exist in the quote-unquote real world, but it does exist. It has to. Otherwise our rule doesn't make sense. All of our rules kind of fall apart. And clearly they don't, because they work for everything else. So we kind of invented this imaginary number, we call it I. We don't give it a Roman, or we don't give it an Arabic Hindu symbol, like 1, 2, 3, 4. It's just called I. And it represents the square root of -1. That's why you never see i's in functions or i's as variables, is because I has a definition. It's the square root of -1. Now here's where the argument comes about. You can multiply real numbers to I. So you can see things like 3i, 12i, 4/3 I, 3.14i, pi I, so on and so forth. Any real number can be multiplied to I. Some people believe that those become imaginary numbers. Some people believe that, some people like myself, say they are just multiples of the only imaginary number. That's a personal choice, however you want to say it, it's fine. But basically, I follows all the rules of multiplication as well. So you can multiply anything you want to I. Actually, I follows all of the equality properties. All of them. You can square I. You can divide I. You can, take the square root of I. You can do anything you want to I that you could to a real number, except write it on the number line. That's the only thing you can't do. That's what I find really, really cool. Anyways, again, geeking out. So the first objective here, now that we've kind of introduced this I thing, maybe you heard it before, maybe you haven't, is we want to take stuff that we haven't been able to simplify before, all those negative square roots, and we want to simplify it using I. Okay, and we're going to think about it in two different parts. So let's say you have something like -9 under the square root, right? Well, if we think about it, that's -9. The -9 is -1 times 9, right? It's -1 times 9. So in other words, using the product rule, we can rewrite that as the square root of -1 times the square root of 9. We know that the square root of -1 is equal to I, and the square root of +9 is equal to +3. And so we arrive at 3 times I. So that's how you can reduce it. You can think of it in two different parts. In other words, the square root of a negative number is equal to I times the square root of that positive number. Okay, let's do another one just to be sure. Square root of -100. Well, I can think of that as the square root of -1 times 100, right? Times a +100. Using product rule, I can say that square root of -1 times square root of 100, and that means I have I times 10, And for simplicity's sake, we usually put coefficient, then I, and then if we had any radicals, we would put radicals at the end. But we end up getting 10i. Same thing, same thing. Let's do it again over here. I've got this negative in front, I'll come back to that, but now I'm going to consider this guy as negative 1 times positive 36. Negative 1 times positive 36 ends up being, oh, sorry about that. Just wanted to hit this back button, now I gotta erase. So I have negative times, let's do 36 times negative 1. And I have negative times square root of 36 times the square root of negative 1. I know that this ends up being 6, right? And it's going to be negative 6 for our negative root. That's why we put the negative out in front. And times I. That would be our final answer. Negative 6i. Let's go down here. Square root of negative 2. Again, I can think of this as the square root of 2 times negative 1. Right? 2 times negative 1 is the same thing as negative 2. Square root of 2 times square root of negative 1 is how it breaks up with product rule. And I end up getting square root of 2 times I. Square root of 2 doesn't really reduce, right? It doesn't really reduce into anything like 6 or 10. And it's a prime, so you can't really reduce it down anymore. So we would just write it like this. And again, for syntax, we would just put I first like a coefficient. And we would draw much prettier than that. Root 2. So it'd be I root 2. So it goes numbers, any whole numbers, i's, and then radicals. Whole numbers, i's, and then radicals. One more, square root of negative 54. Once again, I can consider this in two parts. The square root of 54 times the square root of negative 1. And I just jumped product rule, right? That second part's going to become I. So let's rewrite it up here. Second part's going to become I, but this first part, if we remember, that's going to be 6 and 9. 2 and 3, 3 and 3. Oh my gosh, what is wrong with this test? Okay, 6 and 9, 2 and 3, 3 and 3. I've got a pair, right, because it's squares. I can take a pair out of 3's. I get 3 root 6 times I, otherwise known as 3i root 6. And that's my final answer. Alright, so hopefully this substituting with I thing is kind of making sense. Basically, at the end of the day, if you ever see a negative under the radical, it means you can pull out an I. That's all it means. Let's talk a little bit more. Like I said before, I's obey all the rules except being able to be written on the number line. So you can square I as many times as you want. You can cube I. You can fourth root, or you can take I to the fourth, right? Some things happen. We're talking about the higher powers in a minute. But first, let's talk about I squared. Think about it. If you have I squared, it's the same thing as negative or square root of negative 1 squared. And by our nth power rule, those cancel. You end up with just a negative 1. So that's going to be the only number that when you square it, you get a negative number. That's going to be the only thing you can do. That's why earlier, excuse me, in our extraneous solutions, we ended up getting, when we had things like, 3x, square root of 3x plus 4 is equal to negative 3, right? We would say no real solutions. And we were correct. There are no real solutions to that answer. This would be an imaginary solution, right? That would be an imaginary solution. So there is still a solution, just an imaginary solution. All right. We can use that idea to simplify some stuff, right? Important to note, product rule only applies to real numbers. Product rule only applies to real numbers. I'll say it one more time. Product rule only applies to real numbers. Neither one of these is a real number. Square root of negative 4 and square root of negative 9. These are not real. Not real. That doesn't mean they're not cool. They're just not real. So when we wanted to use product rule, if we wanted to just use product rule willy-nilly, you'd end up getting something like this. You'd put them both under the radical, you'd multiply them, you get a positive 36, and you'd get 6. And you'd be wrong. Here's why. If we reduce it by I, right, you pull out the I part, and you reduce the middle, you end up getting I times 2 times I times 3. Or 6i squared. I squared is negative 1. You end up getting negative 6, not positive 6. And negative 6 does not equal positive 6. So product rule does not apply. use I to simplify. If you ever see a negative, start with I. Just go right and start with I. Don't even worry about your other things first, okay? Start with I. Alright, let's try a few of those out, right? Let's try a few of those out. So I'm going to start with I. Here I've got square root of negative 3. So in other words, 3I. Oh, just kidding. No. I've got the I times the square root of 3. Here I've got negative 7, square root of negative 7. So I times the square root of positive 7. I can multiply these two guys together. Now they're real numbers, right? Now that part is real. Now that part is real. So I can say the square root of 21 times I squared. Or in other words, the square root of 21 times negative 1. Or negative square root of 21. And it becomes a negative root. That's all that's happened. It becomes a negative root. Actually came back to being a real number too, right? It's a real number this time. Let's try it again. So if I ignored the fact that product rule doesn't work here, I would be inclined to say that's a square root of 16 and it's equal to 4, right? Just multiply them together and then it's equal to 4. But let's see what happens when I don't do that. So I have I times root 2 is the simplification of that, times I times root 8, right? I basically just take the negative part out. Take the negative part out. Reorder a little bit. Yeah? Square root of 16 times times I squared. Now that is a 4, but now it's times negative 1. I don't get 4, I get negative 4. I get negative 4 as my answer. And remember, $4 up versus $4 down in your paycheck, that's a big difference, right? If you're paying $4 to your boss, you're gonna be a little mad. Let's do it one more time. We've got one real number and one not real number. So let's start by simplifying this to make it more of a real type looking number. Alright, times root 6. Now I can combine them using product rule, so I get square root of 30. And can I reduce that? Let's see, 3 and 10, 2 and 5? Nope, that is reduced. So that is my answer. So I didn't change this one to an entirely real number, and that's okay. Right? I didn't change it, but that's okay. Okay, we can also divide, right? And same thing, quotient rule only applies to real numbers. It does not apply to negative numbers. So if we change them to what we call complex, well, it's not really complex. They're really still imaginary. Again, it depends on who you talk to. But if we take out the I first, then we can deal with the solely real part as a quotient. So let's start with that. I'm going to change this into, instead of the square root of negative 75, I'll change it to I times the square root of positive 75. And I times the square root of 3. Well, I've got an I divided by an I, and those follow the rules, so they cancel. I get the square root of 75 over the square root of 3. 75 is 5 root 3, because it's 15 times 75, there's 15 times 5 and then 5 times 5. So that's 5 root 3 over root 3. Cancel, I end up getting just a whole 5. So that's cool. That whole thing ended up being 5, right? So using I helped us bring two imaginary numbers back into the real realm and even into the whole number realm. Same thing goes over here. Let's try this one. So I'll take this I times the square root of 32. Square root of 32 I can also reduce down to I times 4 root 2. That's not how I would write it. I would write it 4 I root 2. Let's do that on the side over here. Excuse me. Square root of 32 breaks down into 4 and 8. Which is 2 and 2, 2 and 2 and 2. There's a pair, there's a pair. So I've got 2 times root 2, which is 4 root 2. And the negative part becomes the I. So that's just what I did, sort of kind of in my head. And then I have a positive root 8, right? A positive root 8 reduces the same way down to 2 root 2. Now I can see that those are going to cancel. And the 2 is going to cancel with the 4 to leave a 2 behind. So my final answer is still imaginary, but it's 2i. Much prettier than this whole radical nonsense. 2i. Okay, so those are wholly imaginal numbers, just radicals, monomials, things like that. Excuse me, I'm so sorry. I'm good. Okay, then we've got these things called complex numbers. Complex numbers, as you saw back in our chart, sit above real and imaginary. It's because they're both. They're both. They're two-part numbers. They have an imaginary part and a real part, and they're only expressed as binomials, okay? So they have one part that's solely real, 3, and another part that is wholly imaginary, 4i, right? So it's a combination of the two, and you can have many different combinations. They can be rationals, they can be, pi, they can be cosine, anything you want stick together, as long as there's an I in one of them, but a real part in the other. So the first part's always the real part, the second part is the imaginary part, and that's what complex numbers are. Let's identify the parts of these. Which one would be the real part? It's the part without the imaginary number, right? The imaginary part would be 2i, and the real part would be 4. Whoops. That would be the real part, right? Real, you can put on a number line. 2i, you cannot put on a number line. Over here, this would be the real part, and this would be the imaginary part. Cool. Hopefully that's pretty straightforward. Complex numbers behave like polynomials, like binomials. When you are adding and subtracting them, it just comes down to like terms, right? And you can think of like terms as what parts are real and what parts are imaginary. So let's add or subtract some things. I've got these two complex numbers here. Notice they're separated by parentheses, so you know they are two numbers, right? In other words, two binomials, right? And so I'll just add things that are alike. The real parts, add 2 plus 6 is 8. And the imaginary parts, 3i and 4i, I'm just adding like terms here, right? So I'm not multiplying, it doesn't become I squared. I'll just add the coefficients, 7i. 8 plus 7i is my new complex number. Let's try a subtraction one. I can do this one of two ways. I can just remember that I'm subtracting, but if you're like me and you like to create easy ways for yourself, keep the first one the same, change the second one to the negative version. So distribute it, and then do like terms that way. So adding like terms, 6 plus negative 3 would be 3. Adding the imaginary part, 6 plus negative 2 would be a 3i. Yep. And I get a new complex number, 3 plus 3i. Let's try adding a few of them now. Just go part by part. 4 plus 3 plus negative 6, that would be 7 minus 6 is 1. Add the imaginary parts, 2 minus 1 plus 3, that's 1 plus 3, or 4 imaginary numbers, right? 4 imaginaries. And there's my new complex number. One more time. So add the reals, subtract this time, subtract it, right? So I'm going to rewrite this real fast before I start doing things as 7 minus 3i, that one didn't change, plus 8, plus negative 8, plus 6i, right? Negative and negative. And then this one is still a plus, so that one stays the same as 3 minus 2i. Now, annoyance, there we go. I can add reals, 7, negative 8, and 3. That becomes negative 1 plus 3 is negative 2, plus the imaginary parts, negative 3 plus 6 is 3, minus 2 is 1, so I. 1i. Alright, one more. So I've got these two complex numbers here. I will subtract them. I've got negative 9 plus 4i minus 9 minus 8i. That's going to be negative 18 minus 4i. Let's let's do one other one, just one other one I want you to see real fast. What happens when you have 3 plus 2i minus 3 plus 4i? Okay. So I'm just going to subtract here. The 3 and the 3 cancel to 0, and I get these two canceling to negative 2i. So in this last example that I just made up, because I think that's what I was going for in this one, but anyways, this last example, the real part ended up canceling out. That doesn't mean the imaginary part canceled out. So I was just left with a negative 2i here, a wholly imaginary part. And that happens sometimes. Same thing can happen in the reals, right? Things cancel out all the time. Same thing goes for imaginary numbers and complex numbers. Things cancel. You just end up with entirely imaginary or entirely real. And sometimes that happens. It's nothing to worry about, though. Okay, still quite a bit to go. Next, let's talk about multiplying. Multiplying using the distribution property, as I've said before. This is all jammed into one section because I follows every single rule except being able to be written on a number line, right? Now, that doesn't mean every single imaginary number follows the same rule, but I is a number. It's a number. It's just an imaginary number, okay? So it has to follow all the same rules. So if when I multiply, I distribute. It's the same thing. I multiply the real parts together, I get 8i. Multiply those two together, I get 12 and I squared. I squared is negative 1, so I'll take one additional step. And then I can write this as 12 plus 8i. I'm sorry, negative 12 plus 8i. And I've arrived at the complex number, okay? So it's just distribution. There's only this one extra step you have to worry about. Same thing goes for binomial times binomial, right? We do the same exact thing. You have 4 terms, you match them up. At the end, you may have to multiply, you may have some I squareds you have to take care of, but other than that, it's the same thing. So 3 times 4, it's going to be 12. We'll write it out this first time. 3 times 4 plus, let's do red, 3 times negative 2i plus 5i times 4 and the last one plus 5i times negative 2i. Okay, so we've got 4 terms, 4 combinations. Still what it comes down to. This one becomes 12. Oops. 3 times negative 2i, just multiply the coefficients, negative 6i. Same thing goes with 5i times 4, just multiply the coefficients, plus 20i. And the last one, I multiply the numbers. Oops. 5 times negative 2 would be minus 10, and then I times I would be I squared. Just like if it said x, okay? This is nothing new. It's just like if it said x. Then I go through and I combine some like terms. So I have 12, and we'll come back to that in just a sec. These two guys both have i's, so that would become a 14i, right? 14i. Now here, this 10 is actually 10 times negative 1 now, right? So this is negative 10 times negative 1. It gives me a positive 10 plus the 12, so this will be 12 plus that, right? And then at the very end, I end up getting 22 minus 14i. So I actually do end up getting another complex number, which is cool. Complex number times complex number ends up being complex number. Let's do that again. Let's do that again. 2 times 1, 2. 2 times negative 5i, negative 10i. 3i times 1, plus 3i. 3i times negative 5i, negative 15. And I times I is I squared. Now I've got 2 here. This becomes negative 10i plus 3i is negative 7i. Minus 15 times negative 1, which is what I squared is. Negative 2, let's see, that becomes a positive 15, right? So 17 minus 7i. is my final answer. Let's do it one more time. One more time. Here we got some things that look like conjugates. Interesting. They look like difference of squares. Let's see if that actually happens. Remember, when we have two conjugates, the radical part disappears. Let's see if the I part disappears. Maybe it does. But until then, let's just do it the same way. 3 times 3, 9. 3 times negative 4, negative 12i. 4i times 3, positive 12i. And then we have 4i times negative 4i, negative 16i squared. Lucky ducky. Start combining some stuff. We got 9. Well, these two guys cancel out. That's good. Minus 16i squared. I squared is the same thing as negative 1. So I get 9 plus 16, or 25. Hey, look at that. The imaginary part did go away. So it looks like when you have this kind of form, you end up with a whole number. That's the entire idea behind the conjugate of the complex number. Okay, so that's our entire next section, is that when you have two things that look like conjugates, remember a conjugate, same terms, different signs, you end up with a whole number. But regardless, it's just, you just treat it like a binomial. Treat it like a term, right? Treat it like a term. Okay, let's see if we can divide these guys using their conjugate. So remember, a conjugate is 3 plus 4i, 3 minus 4i, right? Same terms, different sign, different sign. And when you multiply them, we saw that you end up with a wholly real number, an entirely real number. So let's use this idea to divide these guys. Essentially, we're going to be, quote unquote, multiplying by the reciprocal, right? Because that's how you deal with division. You multiply by the reciprocal. The reciprocal, quote unquote, in this case, is the conjugate. So we're going to multiply by 5 minus 2i. What I do to the bottom, I must do to the top. Okay, I got two different complex number situations going on here. So I'm going to start with 5 plus 2i times 5 minus 2i. I'm going to start with the denominator to prove to you that the conjugates end up being a real number. So let's divide by that. Let's multiply those. You get 25. That's plus 10i minus 10i. So plus 10i and minus 10i. And then at the end you have 2 times negative 2, which is negative 4i squared. Here we end up with 25. These guys cancel. Minus 4 times negative 1. So 25 plus 4, or 29. So on the bottom, we end up with an entirely real 29. Entirely real 29. What about the top? Let's try that one now. Let's see. 8 plus 9i times 5 minus 2i. 8 times 5 is 40. 8 times 5 is 40. Plus, I should say minus, because it's a minus, right? Minus 6, so that one. Minus 16i. 9i times 5 is plus 45i. And that one would be negative 8i squared. This one's not going to cancel so much. So 40... Let's see, 45 minus 15, I want to say 29-ish, yeah, 29. So plus 29i minus 8 times negative 1, right, when you convert the I squared. So we get 48 plus 29i. 48 plus 29i is our final answer. Now, just like when you have a binomial, I cannot cancel the top 29 with the bottom 29. Okay, I just can't do it. Because that is part of an addition, it's part of a binomial, it's part of a complex number, right? A complex number, and you can't take pieces of complex numbers. Alright, let's try this one over here. Sorry about that. I had to sit up. Okay, 29 plus 5 over 5 plus I. Well, the conjugate here would be 5 minus I. right? So same terms, different signs. Same term, different operation. 5 minus I. Bottom is probably going to be the more complex one, so let's start with that one. 5I, 5 minus I. That would be 25 minus 5I plus 5I. Those two, and then the last two would be minus I squared. So I get 25, these guys cancel, minus a negative 1, so 25 is 26. On the bottom, I get 26. On the top, I have a monomial times these guys, so 29 times 5 is 145, minus 29I. And that is my final answer. Awesome. Now this is still a complex number, right? Because I could break those into two fractions and reduce them to decimals. There's nothing wrong with having fractions or decimals in a complex number. But, you know, it's not really all that pretty, so I'm just going to leave it as it is. Last one. Let's do this one. What is the conjugate of I? Well, it's not a binomial, so I don't need to find the conjugate of I. I can just divide by I. Remember, when you have a monomial, you can just divide, or you can just split it into two fractions. So this one's really just reducing. I've got 1 over I and I over I. The I over I is going to cancel to 1. Remember, anything is it's going to obey pretty much every rule except being able to be drawn. I can make that one i's to the negative 1 plus 1. That could be probably the easiest way I could write it. I can also write it as 1 over I plus 1. That's fine too. But really, there's not much I can do with that one at the end of the day. It's kind of just rearranging it. All right. The very last thing we're going to talk about is the powers of I. So we've already seen that I squared is pretty important. It becomes negative 1. So I squared is the square of negative 1, square root of negative 1. Cancel, cancel, you just get a whole negative 1, right? So let's make a little running tab here. I is equal to the square root of negative 1. And I squared is equal to the square of that, so just negative 1, right? Let's consider I to the third now. We take it to the third power. We end up getting a negative 1 and a square root of negative 1, or a negative 1i, negative I. In other words, I to the third is negative I. It's negative times I. Because you take out the negative 1 part, you're left with 1 more I, so it's negative I. I to the fourth does something similar. I have 2 of these guys, so I have 2 negative 1s, and it actually goes back to being a positive 1. Same thing here. I've got 2 negative 1s, goes back to being positive 1. I to the fourth is equal to 1. After that, it just repeats. It repeats over and over and over and over again. I'm going to prove it to you. I to the fifth, I can break that into I to the third times I squared, right? Same thing, same thing. I to the third I know is negative I, times I squared is negative 1. I have negative times a negative, that's a positive I, that's the same thing as I to the first. Same thing as I to the first. So I've got I again. Let's do I to the sixth. I to the sixth, if it's following this pattern, what that should end up being is, if that's 5, 6, 7, 8, 9, 10, 11, 12, it should end up being this one, right? Actually, let's do 12. Let's do 12. I changed my mind. Let's do 12. If it follows this pattern, then it should end up being 1, okay? So it should end up being, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it should end up being the same thing as I to the fourth. I to the 12th. Let's see, I can rewrite that as I to the fourth times I to the fourth times I to the fourth. Right, I to the fourth, I to the fourth, I to the fourth. I know I to the fourth is 1, so 1 times 1 times 1. Check that crap out, it did. It actually ended up being it ended up being the same thing as I to the fourth. That's true of any other power of I. Okay, any other power of I, no matter how big you get. Oh, we just did this one. That's cool. So that's equal to 1. Any other power, just you got to divide the power by 4, and you'll see where in the pattern it falls, right? Does it fall at this one? Is it the second slot? Is it the fourth slot? You just got to divide by 4 to see. Now when you divide by 4, you want to make sure you look at the remainder. The remainder will tell you what spot it ends up being. So let's try it on 36. 36 divided by 4. Let's see, let's do that by hand. 36 divided by 4, I can't. That's just 9. Just kidding. We'll do that on the next problem. 36 divided by 4 is going to be 9. That doesn't mean it's in the 9th spot. That means it makes 9 cycles, right? It means it takes it through 9 different times. It's going to go through once, twice, three, blah, 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 blah. But that means it's going to be the same thing as I to the 4th. It ends with the last one on 4. So just like the 12 ended the 3rd cycle, right? 3 times 4 is 12. The 9 times 4, it ends on I to the 4th, so it's going to be in the 4th spot. 1. Let's try it. So now let's try it with this huge number, right? We've got, let's see, 1, 2, 3, 4 billion, 438 billion, 659,000, or so, million, 392,743. So I can't even say that number very well, but we can still find out where it is in the cycle. We can divide that number by 4. When you divide it by 4, it ends up being 1096648 185.75 dot 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 dot. And that's all fine and dandy, but the only part we care about is this 0.75, right? That means the remainder is 3 out of 4. 3 out of 4. So that means it's sitting in the third, it's sitting in the 3rd spot, or it is equal to negative I. That's the only part we cared about. That's it. Alright, so that's what happens when you have positive i's. When you have a negative power, again, the i's have to follow the same exact rules as all of the real ones, right? So this is just the same thing as 1 over I squared. And we know that I squared is negative 1. So we've got 1 over negative 1 or negative 1, right? That's not really all that super impressive. Let's do the same thing with negative 1. Well, that's just 1 over I to the 1st or 1 over I. Okay, cool. Same thing goes with this one now. Now you've got this huge number and it's negative. So this is going to be the same thing as 1 over I to the 3855947,394. And then if we take that and divide it by 4, we can see what spot it is. So 388. So 385594, 385594, 7394, divided by 4, if you have a powerful enough calculator, then you would get 0.25 dot dot dot, and then again the only part we care about is the fact that it's 0.50 dot 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 dot, total dyslexic moment there, 0.50, that's all we care about, 0.50, not 0.2, don't know what's going on with me right now, so 0.50, and that's the only part we care about. We care that it's 1/2 of the way through the pattern, so it'd be equal to y squared. So this would be equal to 1 over I squared, which we just saw in the last example was negative 1. So that huge, 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 huge power boils down to negative 1. Because that's it. That's the only thing I will ever do. Alright. I hope you geeked out as much about complex numbers as I did. I think they're super cool that they follow all these rules and yet they break them all at the same time by not being real. I just think that's a really weird concept and it makes me like geek out for some reason. If you didn't geek out like I did, hopefully you at least understand. I hope this answered your questions. If not, shoot me an email and I will see you next chapter.